had so far. I'll almost certainly do some tweets about the next few talks. It would be lovely to have some shares and likes and things like that, so that would be much appreciated. The second thing to tell you is that we have BBC Look East coming here today. So if you see people wandering around with television cameras, particularly during morning coffee, or indeed in the first session after the afternoon, please look interested, excited, engaged, etc., etc. If anybody has a problem with this, please tell me. But given that we're streaming live for all the seminars, I worked on the assumption that actually probably it would be okay for everybody. So that's just a heads up for what's going on today, and I'm sure it will be a brilliant session as well. Thank you.
Thanks, Steve. Okay, so our first speaker this morning is Nigel Hitchin, who's going to make some remarks on Nahm's equations. Many thanks.
Okay, thank you. Okay, so it's where is he? Oh, here he is.
Yes, I should have waited to make sure.
So it's a great pleasure to be here to speak for Simon's 60th. I first heard about Simon probably in early 1980 when in Oxford, when Ewan James came down and showed me this application for graduate study from a Cambridge student. And he said, look, the letter says that this is the best student we've had for 10 years, you know. And so he said, well, shall we make him an early offer? And indeed, we did. And to our great benefit, Simon came across from Cambridge to Oxford, and he started as a graduate student with me, and then went on with Sir Michael. I've sometimes wondered who the other student 10 years older than Simon was, you know. Anyway, Simon, even as a graduate student, he had original ways of looking at all sorts of things. The topics that I suggested to him, and many other things besides, which he never told me about. So he's, you know, I think as we all know, he's like the iceberg where there's 2/3 of it is, you know, never necessarily sees the light. But actually, there was one occasion when he'd been working on something, and unbeknownst to me, and so I was in the so this was probably in the mid 1980s, and I was in the tea room in Oxford and talking to somebody, and they said, "Oh, Simon gave an interesting lecture in Southampton on Friday." And I said, "Oh yeah, what was it all about?" They said, "Well, it's about your work, you know." I said, "What, really?" And this was the his work on harmonic maps from surfaces, equivariant harmonic maps, which provided, in fact, for me, the missing link in the whole circle of ideas involving, which now are called the Higgs bundles. So eventually he told me about it, but so there's, as we all know, there's far more to Simon than we see in his papers. Anyway, I wondered what to talk about today. So I thought of looking at one thing which Simon has, in fact, looked at on a number of occasions. These are Nahm's equations. So this is certainly not, well, there may be some symplectic aspects to it, but it's not kind of mainstream in his work. But there are several papers where, in one form or another, Nahm's equations appear. I mean, probably the most influential was this one, Nahm's equations and the classification of monopoles, where he used Nahm's equations to show that the moduli space of SU2 monopoles was you can also describe as in terms of rational maps. But then there are other types of Nahm's. Sometimes, in fact, there's this one here about Ashtakar's equations. This was another comment that I remember from him. We've been reading this paper in Communications in Mathematical Physics by relativists, Ashtakar, Jacobson, and Smolin. And I remember him commenting, you know, this is Nahm's equations with for the diffeomorphism group of a 3-manifold. And so these kind of insights lead to all sorts of issues. So I think these are various papers of Simon where in one form or another Nahm's equations have appeared. But I want to consider the I want to kind of put a new light on Nahm's equations and ask some rather different questions about them. So what are they? Well, these are ordinary differential equations, very symmetrical ones. For a triple of matrices. So the matrices depend on the function t, and they evolve according to these very symmetrical equations. And you can think of them in many different ways. One of them is to say it's the self-dual Yang-Mills equations on R4, which are invariant under 3 translations. This is part of the whole picture of dimensional reduction of self-dual Yang-Mills. But they appear in lots of different ways. I mean, for the 2x2 matrices, these are essentially Euler's equations for a spinning top. You could also think of these as kind of the zero set of an infinite dimensional hyperkähler moment map. They have been used in many ways, starting with Peter Kronheimer's work in producing hyperkähler metrics on coadjoint orbits, and then anyway, there's lots and lots of ways in which they appear in geometrical problems related to gauge theory. But I want to, so my different point of view on these is through generalized geometry. So I'm not going to say very much about this. So generalized geometry involves thinking of replacing the tangent bundle manifold by the direct sum of t and t star, thinking of that as having an orthogonal structure of signature n comma n, just the the evaluation of one on the other, and then the extra issue that comes in is this extra symmetry or transformation in the B field. If I have a closed 2 form, then that acts on t plus t star, preserving the orthogonal structure, and we have to think of this as some additional symmetry beyond the obvious diffeomorphism invariance of t plus t star. So within this situation, there's a notion of a generalized complex structure, which at one extreme is a symplectic structure, at another extreme is an ordinary complex structure. And I'm going to just think of the complex structure end of things. So I won't say exactly what it is, but one of the features is that if we think of an ordinary complex structure as a generalized complex structure, then this B field action becomes a symmetry. So if I have a closed 1-1 form now, then that is a symmetry of the generalized complex structure. So this puts it on the same footing as symplectic geometry, in the sense that if I take a function, I can take dd bar of the function, and that becomes a symmetry. So there are Hamiltonian symmetries, if you like, of ordinary complex structures within this context. Of course, they're not acting on the manifold itself, but they are symmetries of anything which is, or they transform anything which is described entirely in this language. Okay. So, so if we take an ordinary complex structure, then you can ask, what does it mean to have a generalized holomorphic bundle? What is it? I mean, is it just an ordinary holomorphic vector bundle? And the answer is it's not quite. I mean, part of the data is a holomorphic vector bundle, but there's an extra piece, which could, of course, be 0. And this is a holomorphic section of the endomorphism bundle of V tensored with the tangent bundle. And it has to satisfy this condition here. So what this means is that the individual components commute, if you like. If you look at the components given the basis for t, then they have to all commute. So this is very similar to something which I've been looking at for many, many years, 30 years or more, the idea of a Higgs bundle. This is a holomorphic vector bundle with now a section of the endomorphism bundle tensored with the cotangent bundle, satisfying this condition. So the one way of looking at these things is to call this, it's not a name that I particularly like, call it a co-Higgs bundle. You replace the cotangent bundle by its co-object, the tangent bundle. Okay, and a former student of mine, Steve Ryan, a few years ago wrote his thesis on these objects. So I'm going to just consider the simplest possible example of this, and that is where the complex manifold is the projective line. So now the tangent bundle is a line bundle, degree 2, O2, and any holomorphic vector bundle is a direct sum of line bundles. So this is the standard. So I could think, if you like, of, well, I'm going to call it a Higgs field still. So this section of the endomorphism bundle tensor with the tangent bundle. This is, I can write it down explicitly if I've got the direct sum. You can write it down as a matrix whose entries are polynomials of various degrees in the affine parameter on the projective line. But more invariantly, if I can take the characteristic polynomial of this, and then the coefficients of this characteristic polynomial are sections of powers of the O1, so these are polynomials of degree 2k as n goes from 1 to k. So if we do this, then we're in a situation where we have a rank V, a rank k bundle, V, over the projective line, and there's a notion of stability, not of the bundle, but of joint stability between the bundle and the Higgs field. So actually I have to say this joint stability condition in the context of Higgs bundles was also suggested to me by Simon. I was trying to explain in the early days of Higgs bundles, I was trying to explain to him on the blackboard why the bundle itself should be stable, and I got stuck, and then Simon mentioned, well, there's a joint stability condition, which was obvious when you really thought about it. Anyway, this is the context here. So we can actually, if we impose this stability condition, which is all to do with the slope of invariant subbundles, then we get a moduli space, and the coefficients of the characteristic polynomial give us a projection onto this vector space. This is the sum of all these powers here, and the generic fiber is the Jacobian of the curve, which is given by this characteristic polynomial. So it's we call it the spectral curve. It's a curve inside the total space of the tangent bundle of P1, and it has genus k minus 1 squared. So there is a moduli space, a gauge theoretic moduli space for these co-Higgs bundles. The simplest, the nicest example is probably this, where you take co-prime situations. So the rank is 2 and the degree is minus 1. So typically in moduli spaces, this is an example where there aren't any semi-stable objects. And so the moduli space is smooth, and what it turns out to be here is actually the universal elliptic curve. So I've now written my Higgs field as a matrix, and the alpha, beta, and gamma are polynomials of various degrees. Gamma is of degree 1, so it has a unique 0, Z0. You evaluate alpha at Z0, that's well defined. Alpha itself is not quite well defined because, okay, the O here, the maximum degree subbundle is uniquely determined, but this one is not. But anyway, the value of gamma at Z0 is uniquely defined, and okay. And so actually it's this, you have this universal family of elliptic curves. The generic fiber is the Jacobian of the elliptic curve. Okay, so what's this got to do with Nahm's equation? As I said, that the B field action, so if I have a closed 2 form on, in this case, P1, then it will act automatically as a symmetry of the generalized complex structure, which means it's an action on, it takes a generalized holomorphic bundle to a generalized holomorphic bundle. It gives me an action on the moduli space. So any closed 1-1 form on P1 will actually act as a symmetry of the picture. It will be it'll give me a holomorphic transformation of this moduli space. And this is what you do. So this is the way it works. That if we think of the holomorphic structure on V, as let me call that D bar, then I change it to another one by contracting my 1-1 form with this vector valued, so this endomorphism with values in the tangent bundle. So I contract the tangent bundle part with the cotangent part of this, and I get a 0-1 form with values in the endomorphisms. That's just what I need to change the D bar operator. So I have a new D bar operator, which is given by this contraction, and the Higgs field itself remains the same. So this is the B field action, and the fact that this holds, and together with the fact that phi is holomorphic, tells me that actually this is integrable. Well, it tells me that this is actually not just that this is true, but also that this is an integrable complex structure. Although, of course, in P1 it doesn't really matter. If I change my 1-1 form, if I make it if it's cohomologically trivial, if it's D bar of a 1-0 form, then this generates a holomorphic equivalence. So within the moduli space of these objects, it's only the cohomology class of the 1-1 form on P1 in this case, which gives us this transformation. So cohomology class, so it's just H2 of P1, it's just one-dimensional. And so we have this canonical action of the B field on this moduli space of bundles. And so this is what I call the Nahm flow. It's a one-parameter group of transformations, holomorphic transformations of this moduli space of co-Higgs bundles. So if I take now a vector bundle V which is holomorphically trivial, which is in the case of degree 0 you would say is the generic situation, then I can write my Higgs field as a quadratic polynomial with matrix coefficients, and I put them in this form, and so I put in the d by dz just to make it look like well, it's the invariant way of writing it as a section of the tangent bundle tensored with the matrices. And of course I take a closed non-zero 2 form, cohomology class is non-zero. And then the theorem is that actually as I vary B through parameter t, if this d bar operator, if it's holomorphically trivial, then there's a choice of trivialization such that these Ti satisfy Nahm's equation. So the upshot of this is that in this situation, Nahm's equations consist of, it's the natural action of the B field on this moduli space of generalized holomorphic structures.
So that will be always true for small t.
Yes, that's right. So as t goes along, you may encounter, that's right. But on the other hand, okay, that's a good point, that doesn't affect the moduli space. So although V is holomorphically trivial if you get Nahm's equations, then of course within the moduli space itself, the fact that V might jump from one holomorphic structure to another doesn't affect things. I'm not fixing the holomorphic. I mean, I'm fixing the pair. I'm looking at the moduli space of pairs of objects. That's right. So long as this, so on whatever interval this is, for which this is holomorphically trivial, then we get a solution to Nahm's equation. So this, I mean, it's an elementary proof. So let me give you this elementary proof of it. So we start with t equals 0. So we start with psi. This is a Higgs field in this setting, and V is trivial. So the assumption that V is trivial for all t means that this new d bar operator is, if you like, pure gauge, which means that this contraction here, which is the B field action, is G inverse d bar G for some complex gauge transformation. And the psi is now going to become time, so this is a time-dependent gauge transformation, and then psi is related, so psi is constant, but it defines a phi which is time-dependent according to this gauge transformation. So if you differentiate with respect to t, you get this. And now we take the obvious two form, if you like, the area form, the volume form of the two-sphere, and then do the contraction with phi, and you get this. Now so we want to look at d bar. We want to solve this equation. Where are we? So we want to write this as d bar of something. So you do the most obvious thing, which is to integrate naively with respect to z bar, and you get this term, which of course has singularities at z equals 0, but then you add on these holomorphic, or these meromorphic terms, if you like, in order to make this smooth. And then you obviously differentiate this with respect to t, you get this. And now we just got that this was equal to this, so you put that in there and equate coefficients, and you get Nahm's equations. So this kind of B field action makes it rather easy to see that you get Nahm's equations this way. So what are the properties when you do it this way? Well, one is that, well, the psi itself, of course, so phi is gauge equivalent to something constant. So that means that the coefficients of the characteristic polynomial are preserved, because it's the same as the characteristic polynomial of psi. And that means that under this projection of the moduli space onto the vector space here, which is given by the coefficients of the characteristic polynomial, the vector field lies along the fibers. And here's the point that we don't actually need to assume now that V is non-trivial, that the flow still makes sense. And in fact, if you look at the generic picture, if you look in higher rank, then of course the different possibilities that if the degree is d, where d is between the 0 and k, then the generic splitting type looks something like this. And then you have a corresponding set of equations. So these are not exactly Nahm's equations, but anyway, they appear in exactly the same way. In fact, it turns out that even if you're only interested in Nahm's equations, when the spectral curve becomes degenerate in the sense of being a multiple, where the characteristic polynomial has a multiplicity, then you actually need these kind of modified Nahm's equations to write down a solution to the ordinary one. Anyway, so in this rank 2 example, this standard rank 2 example, the universal elliptic curve, then the Nahm flow is this standard, if you like, vector field, non-vanishing vector field on the elliptic curve, on the fiber, the generic fiber. So, so what happens? So, what is the traditional way of solving Nahm's equation? So, let me start by asking the question that really was motivating me in this. So, we have this moduli space, and we have this vector field on it generating this flow. And the obvious question to ask is, what are the fixed points of that flow? What are the zeros of that holomorphic vector field? If we only restrict to the non-singular fibers, then it's a holomorphic vector field on a torus which has no zeros. So the issue is trying to understand, if we want to try and understand the fixed points of this flow, then we need to understand what it means to look for the data that goes into Nahm's equations, and to understand what goes wrong. So here is, if you like, what I would call the traditional way of thinking of solutions to Nahm's equations. So we start with the characteristic polynomial, which is described as this algebraic curve inside the tangent bundle of the projective line. And so x is, we think of x as being an eigenvalue of phi, a multiple valued eigenvalue, so multiple valued as a function of z, but it's single valued on the spectral curve. And so the curve inside this total space of O2 is a degree n covering, this is a rank n bundle, degree n covering of P1. So what you do is that you take a line bundle on the spectral curve, take its direct image, which gives us a rank n vector bundle on P1. You work out the degree by various means. And now we take, so x is essentially the tautological section. So when you pull back the bundle O2 to its total space, then there's a tautological section of that pullback. That's basically what x is. And then you take the direct image of x, and that defines you the Higgs field. So if we now want to understand this from the point of view of the B field, so if we think of now the local coordinates on the tangent bundle, then this x is this tautological section is basically this object. And the B field action on the direct image is, so we know what it is in concrete d bar terms, so you can transform that into the d bar operator on the line bundle upstairs, and all it involves is adding on this term. So what is this term? This is the contraction of this section of the tangent bundle, or the pullback of the tangent bundle, with dz bar over 1 plus z bar squared. So this is now a linear flow, because this is linear in t. This is a linear flow on the Jacobian of S, and that's basically what the B field action is, or what the Nahm flow is, that you take this one parameter family, if you like, of, so this gives me an element in, okay, maybe it's better to say it this way, that this gives me a Dolbeau class in the H1O of this non-compact algebraic surface, and if I exponentiate t times this, then I get a one parameter group of line bundles, and the Nahm flow is restricting that to S and tensoring a given line bundle by this and taking its direct image. So this is what I would say is the, if you like, the traditional view, which I always had, of Nahm's equation. On the other hand, in this context of looking at a vector field on a moduli space, this will never give us any zeros of the vector field. There'll never be any fixed points. Why is that? That's because that's because this, of course, is tensoring with a line bundle on the Jacobian, and that's a linear flow. It doesn't have zeros, or it would have zeros if this class restricted to 0, but as we'll see in a few minutes, that never happens. So the issue here is, how do we understand the fixed points outside of this what you would call this traditional integral system point of view on Nahm's equation. So okay, so now let's go back a little bit then to fixed points. What do I mean by fixed points in the context of Nahm's equations? Well, I don't actually mean that the derivatives are equal to 0. I mean, that of course is a fixed point, and that's a very strong condition. But I'm looking at a fixed point in the moduli space, which is solutions up to gauge equivalence, if you like, up to conjugation. So that really puts me back in this situation here. That if I'm really so these are self-dual Yang-Mills equations invariant under 3 translations. A fixed point would correspond to solutions which are invariant under 4 translations. If you like, it's replacing the derivative by an infinitesimal gauge transformation T0. So these are self-dual Yang-Mills equations invariant under 3 translations. Now, are there any such solutions? Well, traditionally we will be looking at the situation where the t's take values in the Lie algebra of a compact group, and in fact there aren't any non-trivial solutions there. So what it comes down to is that because I've set the whole thing in the complex setting, then the fixed points are essentially going to correspond to certainly to complex values of these TIs. So let me just say why. One reason why, if you take these TIs to have values in a compact Lie algebra, then you get 0. You can do it, of course, algebraically. Well, you don't. You get something trivial anyway. But there's a gauge theoretic way of doing it. So think of it this way: if they are invariant under translations, then what we know is that the solutions to self-dual Yang-Mills, which are invariant under one translation, these give us the Bogomolny equations. So if I look at an invariant solution, I could a translation invariant solution, I could put it all on a torus, but basically there are no magnetic monopoles on a compact three-dimensional manifold unless they have singularities because of the Bianchi identity. So you can use, if you like, gauge theory in this setting to show that there are no non-trivial solutions. So this of course is the zero set of a hyperkähler moment map for the Lie algebra tensored with the quaternion. So anyway, all I'm saying is that when I talk about fixed points of this Nahm flow, I'm really talking about complex objects and not restricting to any real Lie algebra. So the point is this, that actually so if I'm really looking at the Jacobian of the spectral curve, then this flow has no fixed point. Even if the curve is singular, the Jacobian, even though it's non-compact, the Jacobian is still a group, and this additive flow has no fixed points because you can show quite easily that the cohomology class of this, so this is the cohomology class on the tangent bundle P1, that it restricts non-trivially to the spectral curve, even if it's a singular spectral curve. So what happens to the geometry, to the algebraic geometry, in order to get fixed points? So the answer is that, well, first of all, obviously the spectral curve must be singular, but when we talk about line bundles, that's not the full story. That you should look at the direct image of a rank 1 torsion-free sheaf on this singular curve. So in terms of the moduli space, the map to the vector space is actually proper. So even if you have a point on the base which gives us a singular spectral curve, the Jacobian is non-compact, but you compactify it with rank 1 torsion-free sheaf. So in order to get a fixed point, then we take the rank 1 torsion-free sheaf on this singular curve, and then we tensor it by this one-parameter family of line bundles, and we have to have a fixed point of that action. Now, fortunately, there's a way of reducing this to a question of line bundles, at least if the spectral curve, although it's singular, if it's reduced. So a rank 1 torsion-free sheaf on the singular curve is actually the direct image of a line bundle on the normalization, or on some normalization, because it could be it could be still a line bundle on partial normalization. So if we want the pullback of LT to be trivial on this, then if this is trivial on the normalization, or partial normalization, then we will get a fixed point, because you're pushing down from the normalization. So the issue is this, that we're looking for normalizations or partial normalizations of the singular curve for which this pulled back line bundle is trivial. They will correspond to fixed points of this action. So what happens? Well, this class here, so what are we looking at? We're looking at a class in H1 of the tangent bundle here. We're looking at its restriction to a singular spectral curve, and then we want to pull it back. So, but there's a geometry, which a rather familiar geometry here, which gives us an interpretation of it. So here is this class here, cohomology class. This is it defines you a principal bundle, translation bundle, if you like, C bundle, Z over dp1. And if the pullback of this class to the singular spectral curve is 0 on this covering, this partial desingularization, then that means that the class is equal to 0, and so it's equivalent to saying that S tilde lifts into this principal bundle. So this classifies principal C bundles. We pull it back to S tilde. It's trivial, therefore this class is 0. So this is a lifting. It gives us a trivialization of this bundle over here. So if you're around in Oxford in the early 1980s, then this picture was actually very familiar in twistor theoretic terms. So actually, so here is the original Penrose twistor space. And you take the projective 3 space and you remove a line, and it identifies this complement with the total space of the vector bundle O1 plus O1 over P1. And there's a free C action, which is this. So what we're saying is basically this is the twistor space of R4, or we're not putting a real structure in, twistor space of C4. We're looking at the translation on C4, which takes us down to C3. Then in twistor theoretic terms, that is the C action here, where we're looking at a non-vanishing section of O1 plus O1, and we're dividing out by translation by that non-vanishing section. So, and then the quotient space is actually isomorphic to O2. You can see that concretely because that quadratic function is invariant under this translation. So, so just a small calculation that actually this C bundle over O2 is defined by this class. So in fact, this is, if you like, this is the trivial U1 monopole, just a constant Higgs field on R3, if you think of it in Penrose-Ward terms. So what does this mean? This means that actually the pullback of this family of line bundles is trivial on S tilde if this covering, if this desingularization lifts to projective 3 space, basically. And so then, we could have, of course, here a non-singular curve inside P3, and the singularities under this, when we project, there'll be singularities, because there'll be points which are equivalent under this translation action in P3. So basically the study of fixed points of this Nahm flow corresponds to looking at curves with sheaves on them inside this inside projective 3 space curve. And well, I haven't imposed any conditions about getting stability and so forth, but quite clearly, since we know that the Hilbert scheme of space curves in P3 is very complicated, it's a rather complicated question to understand fully the zeros of this Nahm flow. So there's another point of view here, which puts it in a slightly different context as well. So if we look at these equations, so now remember we have to think of these as complex matrices now. Then if you replace, so if I replace the T1, T2, T3 by the quadratic polynomial phi is quadratic in Z, and the T0 becomes a psi, then I can write this in this form here. at least this implies, this implies this expression here, which means that this, if I write it this way, this phi minus commutes with phi. Now, there's another one, call it phi plus, which is this, so I subtract this and divide by z. So what's the point about this? These are now linear in z rather than quadratic in z. And the sum of them is equal to phi, so each of them commutes with each other. Phi plus and phi minus commute. So what we have here, we have a pair of commuting sections of O1 with values in the values in the matrices. They define a sheaf on O1 supported on a curve. So this is well, let's put it this way. The original picture of looking in higher dimensions, the picture advanced by Simpson in the Higgs bundle point of view, was to take a Higgs field with values in the cotangent bundle, which satisfies this, and Simpson, his reinterpretation of that was basically a sheaf on a curve in the cotangent bundle of a surface. So here we're on P1, we're replacing the cotangent bundle by a rank 2 vector bundle, E, and the same conditions actually give us this curve with a sheaf on it. So anyway, so it turns out then that if we really want to study fixed points of this Nahm flow, then we're actually looking at space curves and sheaves over them, or sheaves defined by such an algebraic object. Well, my first sort of encounter with Nahm's equations, which was trying to understand Nahm's original paper on monopoles, was in a way my first contact with integrable systems. And that led on to Higgs bundles themselves. So we could follow the same idea in perhaps a rather more interesting situation of Higgs bundles. So now, in the last quarter of an hour, let me revert to the original, well, picture, if you like, of having now not the projected line, but having a higher genus Riemann surface, and a holomorphic vector bundle V over it of rank n. And now the Higgs field takes values in the cotangent bundle, so I write that as a canonical bundle of sigma. And then we have a stability condition which gives us a moduli space, and this moduli space now is holomorphic symplectic. So in the Nahm situation, it's not. If you have, I mean, the fact that this is the cotangent bundle rather than the tangent bundle means that we have a symplectic structure on this moduli space. And now the same procedure, well, actually I've written it in a rather different way this time, but if we look at the invariant polynomials of the Higgs field, and I've chosen this particular basis, then this defines a map to a fibration from this total space, a symplectic manifold onto this vector space. So it's analogous to the, it is basically given by the coefficients of the characteristic polynomial, but they are related to these by some universal relations. Then, if I call that A, this is the base of this fibration, then an element in the dual space of this defines a function on M, which defines a Hamiltonian vector field, and then it turns out that all these Hamiltonian vector fields commute, and so what we get is an integrable system. And the characteristic polynomial now, so the coefficients of this are universal polynomials in this. Now X is a tautological section of this pullback on the total space of the canonical bundle. You can also think of that as the canonical one form on the cotangent bundle. And this is the equation of the spectral curve. So the picture is essentially the same. So in this case, so here is actually an explicit formula for, doesn't really matter so much. So the point is this, that by said duality, this space of functions is given by this vector space, this sum of cohomology classes, and a cohomology class in here defines a cohomology class in the total space. I called it S here. That's the total space of the. Oh, sorry. This is S is a spectral curve. The tangent space, the Jacobian, is of course this, and so the actual along the Jacobian, the actual flow is this. Actually, this is not so much relevant. So in this case, we have the same situation, that actually this cohomology class, this sheaf cohomology class, Dolbeau cohomology class on S, is actually the restriction of one from the cotangent bundle. X here is the tautological section on the tautological one form on the cotangent bundle. I'm contracting it, or I'm multiplying it by pullbacks of sections of various things here. So it actually lives on the cotangent bundle, and therefore defines a principal C bundle over the total space of the cotangent bundle. So, so if we're looking now at the analog of the fixed points of the Nahm flow, we're looking at the analog of the zeros of the vector field, which gives us the Nahm flow. In this situation, we're looking at the zeros of the Hamiltonian vector field for a function f, which is a critical point of f. So we're looking at the critical locus of a function f given by something of this form. So, but the conclusion is the same, that actually, if we're looking for critical points of these functions given by the integrable system, then they correspond to rank 1 torsion-free sheaves on a curve in this total space here of this principal C bundle over K. Now, K is, in fact, a Calabi-Yau threefold. That's easy because in the total space in the cotangent bundle is symplectic. Here we've got a principal C bundle. So actually, if we want to understand the singularities, the critical locus of the Higgs bundle integrable system, and then we're looking at curves inside a Calabi-Yau threefold. Now, interestingly enough, as I understand it, for a different Calabi-Yau threefolds, the local structure of the moduli space of curves and sheaves actually is the critical locus for some function. So here we're going the other way around. I have a function on a symplectic manifold. I am looking for its critical locus, and it turns out to be correspond to curves in a Calabi-Yau threefold. Well, that's a slightly different picture, but the conclusion is that there are that looking for these fixed points, looking at the Nahm flow, becomes a rather complicated situation if you reformulate it in terms of algebraic geometry. Well, I seem to be going too fast, but still, here is, I want to finish with, okay.
Ah, yes.
So, you see, Simon's paper was Nahm's equations and the classification of monopoles. So, I think the classification fails in this case. So, I don't know whether you've tasted these, Simon. I can tell you about the blue top and the gold top. But anyway, I'm sure your birthday is a good opportunity for classifying these monopoles.
Many thanks, Nigel. So, any questions?
An interpretation of these four matrices satisfying the commutator.
Yeah.
I could go directly to that, to an instant on R4, which would give a holomorphic bundle on the twistor space. I'm wondering if that curve is related to that holomorphic bundle.
I wondered that too, and so when I gave a similar talk to this, I have to confess, before coming here. That was for Roger Penrose's 85th, was it? Anyway. where I was asking myself.
I heard that talk.
Yeah, you probably did.
Nice,
Yeah. Yeah. So indeed, I wondered exactly that. I think the picture is rather different. So I mean, you can write down. I mean, you can write down a transition function. So basically, the transition function for the bundle on P3, or you know, I mean, so you or O1 plus O1 on P3. You can write down as basically some transcendental, some exponentials involving the matrices, quite concretely. I think that kind of transcendence rather militates against, I mean, there's no obvious way that I could see to relate that to something which is essentially algebraic coming from the spectral curve. But I mean, I certainly wondered about that because it would have tied things up nicely for Roger, but I don't think it did.
Nigel, marvellous talk, reminds me of good old days. Yes. Especially seeing these bottles of monopoles. I think I remember getting a collection on some other birthday. And your talk brought back all those nice periods when we were all young. I felt a couple of comments. You kept for reference to the B field, you kept the physics only in the background. Okay. I got two comments. One is that the Nahm equation says something's commutative to the zero on the right-hand side. There are, of course, generalizations of that when you put something on the right-hand side. That leads into a whole lot of new areas which are very interesting and you know about them, we've discussed. That's one direction one can go, which includes, for example, replacing monopoles in Euclidean space or monopoles in hyperbolic space and all that goes with it. The other direction, which is rather more exciting in a way, is to go down the opposite route of trying to relate these things to number theory. And there you don't want, well, listen to my talk. I mean, your talk is an introduction to my talk, so it's very convenient. I'm asking myself a question in advance. When you think of, if you were doing this flow on things like, you tend to get flows going through rational points in the circle. If you focus on those and throw away the transcendental part, then you can go down the route of number theory and get to corresponding things which are related to number theory. Going down that route, you will certainly shortly see the vials as proof of the Fermat theorem. I mean, there are lots of hidden things in number theory just behind the monopole. So those monopoles can be used for another birthday later on.
Okay.
Okay, any other questions? If not, let's thank Nigel again.